Okay, so let me start again. So welcome to the course. And now you also got the piece of kit. Good, you will be needing this and also the, hi Manfred. Ah, excellent, excellent. Thank you, sir. Okay, another time. Okay, so welcome again. So yeah, course website you find already. So and you have the piece of kit. So you basically have already almost everything. Only my small part of this course, which is just some show, helping you to go through the exercises. This is very hands-on course, not too much of theory. We just go directly and start playing with this stuff. And yeah, I like it too. Yeah, if you're using your own computer, then you need also the design software, which can be found from the Cypress website. It takes for a while to download it. It took something like half an hour yesterday, or yeah. So it's the PSOC designer, not designer. Yeah, not creator. Not this. Well, we'll we will find it out. Okay, I've been using that so many times I don't remember the name anymore. But anyway, so a couple of things. What is PSOC overall? So let me go to a different view here. All right. So what is this PSOC actually all about? It's about that kind of system. So it's a small 8-bit microcontroller, which also, well, has the normal microcontroller environment. It has I/O ports. It has the clock system. Actually, this one has is quite nice. It has different kind of clock sources you can select from, and then just a simple RISC core. They're using M8C core, which is some sort of variant of ancient M8 processor. But anyways, what makes it really different kind of system is that it also have the digital system, which is fundamentally 8-bit, made of 8-bit blocks that can be configured to do all sorts of things. And also, what is even more weird is this analogous system. So not too many microcontrollers actually have any continuous time analog functions as this one has. So it has basically the CT blocks down there. Those are the continuous time processing blocks, and then it also has the switch capacitor type of processing blocks. So with continuous time blocks, you can make linear amplifiers, and then the and also the comparators, such kind of things. And switch capacitor type of block, you can make A to D converters of different configuration, meaning you can make, for example, select the sigma delta type of A to D, integrating kind of the A to D, or successive approximation kind of A to D by mixing and matching those blocks. Okay, and then it also have the analog reference bus. So there's actually a kind of internal there's an internal band gap, meaning that it has a reference voltage there and also multiplies of that one. and a switch matrix that you can actually run this analog system as unipolar or bipolar biased to the reference levels, and also it you can also mix and match and connect those blocks internally using the switch matrix. So and in addition to that, you can actually have 8-channel multiplexer, analog multiplexer. So you can have one single A to D converter and run 8 different channels to it. Okay, so this the system basically is a mixed signal system. It's designed to be a mixed signal system. So this you can use anywhere where you need mixed signal systems. If you need only digital system, this is not necessarily the best processor for that one. Yeah, okay. It is a good processor for also, say, digital only signals, but well, a couple of things. This is a rare processor, only one manufacturer, although it's a big manufacturer, but we have seen giants to fall. So that's the biggest one. And then of course, when it's rare, then it means that you can find cheaper processors which don't have the analog systems. Okay. And you have a question? Yes. Mm-hmm. AVR, yes, that's the industry norm more or less on doing 8-bit systems. Yes. Yeah, there is a difference. There is a big difference, actually. We will go into that one with a design tool. So AVR is also a very good processor. It can be used. It is used in plenty of places. I think it's almost as usual as the that 8051 core. Yeah, almost. So Intel 8051, which was designed, when the dinosaurs ruled the earth. Yeah, I'm also a dinosaur, so but I'm not ruling anymore. I let the digital people do it. Okay, so dinosaurs were still alive when the core was done, and for example, the 8051 became industry standard because of keyboards. It was the keyboard processor. Yep. And there's absolutely nothing wrong with the 8051 type of core. Actually, the PSOC 3. So we are using here the PSOC 1s. But as you can see from here, there's also version 3, which is a 8051 core running on a at the same clock rate, but it takes only 2 or 3 clock cycles to do this instruction. As in the PSOC core, it uses usually several more clock cycles, so it's faster processor. 81. Yes, PSOC 3, version 3. Yes, PSOC 5. That's ARM core. Yeah, Cortex something. Okay, but anyways, another thing. Okay, system resources here. All of these are, well, not in every single piece of code, but let's see, I/O analog multiplexer. That you can actually find from from all the circuits which has analog systems. Then this is, some of the devices actually have USB. Not these devices what we have here, but they have specific devices for doing USB, and that's probably the easiest USB device you can make is with the PSOC, since the tools are just excellent. They bought the advanced networking, so some sort of I don't remember what was the company, but they bought the PSOC. They bought the USB device kind of thingy from another company, and that's the easiest way of generating. Yeah, USB. Yeah. That's the that stick actually, which was there probably, was it? That's PSOC 5, and yeah, it has USB. Okay. Yeah, and PSOC 4 is also available. Okay, internal voltage references. There's also switch mode pump, so you can actually run some of these devices with a 1.5 volt battery, single standard cell battery. It has a switch mode pump to pump that 1 to 3 or 5 volts. Power reset and low voltage detection, that's on all systems, so to prevent the brownout of the circuit. You can still do the brownout. I actually managed to do my first brownout of the Cypress, the piece of circuits just a couple of weeks ago. Okay, I was measuring the current that device takes, and I didn't do the good job on measuring it. So I got brownout. It means that after that you can scrap the circuit. I2C, that's in all devices. That's a standard I2C kind of thing. Actually, for programmer point of view, this piece of circuit is a EEPROM on I2C. It downloads the code to the code memory. Decimators, meaning you can do the downsampling of the clock speed. Oh, right, some of these actually have also the multiply accumulate processing part. Not all, but I think most of the piece of processors have. Meaning that you can do some, say, decent filtering also with this processor. Yeah, and then a selection of digital clocks. Complex system, and which doesn't show up here, is the big switch matrix to actually connect these blocks and those blocks and I/O. But that we can do on the design software. Wow. Okay. How come that can actually happen? That's interesting effect. Yeah. 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 Yes. Yeah. So that one kind of burned there. All right. Okay. So let's take a quick look at what the course is all about. Then we have now 4 days. I have 5 days of show here in any case. So don't worry, I will just speed up. So fundamentals, today's exercise is about basically getting used to the design environment, nothing more, and how all of these the topics actually are covered. There were some couple of useful links you can browse yourself, look for help. When you are starting to install the PSOC designer, yes, PSOC designer. basically there in some Windows 7 systems, you would get some problems with the one package, which is the graphics package for the designer, and there's some help on that one. If I use a whiteboard, I usually also take the whiteboard pictures and put them there. Will appear here later. Okay, live stream, YouTube. Yes, I'm streaming it as I'm speaking. I'm not I'm not making video of you at all, so don't worry. Unless you really make some funny faces there. Okay. Yeah, no. So I'm just videoing myself and what I'm doing here. So if I make a mistake, it will be there on online the rest of my life. So well, it doesn't prevent me of making mistakes, though. Okay. Each of these topics has also a exercise. These exercises are like that, and it's a Google document, and of course, if you have a Google account, you can also make a copy of that to you. Journey use. All the material I have here is basically Creative Commons license for non-profit use. So academic non-profit use, it's free for anyone to use. You can share with their friends. Don't take any money out of it. Don't sell it. First of all, if your friend finds out that it was free somewhere, he would be really mad at you. And then I will find out that you sold it somewhere. I will come with my lawyer. Okay. And then we'll see how big is your lawyer. Okay. But anyways, so there are some tasks here, like follow the leader and doing stuff. Then how to put an LED there, how to make it blink. Okay, pin input, how to get I/O, digital I/O into the chip, so that LED actually is just a digital output. Pin input is digital input. LCD display, okay, you need somehow to debug your code. Easiest way on this piece of is, since we do not have the total debugging environment on IDE, that means that you need to do some, software debugging, meaning just printing some text on the LCD. Okay, all the exercises. I require actually links. I don't care much about where you put those files somewhere on the cloud services. Dropbox would do fine. If you are familiar with GitHub, sure, why not? As long as I have access to it. So I can download the whole piece of project to my computer, that I can test that what you did actually works. Okay, then again, I don't care about where you put this one, on which form, the main.c routine, basically, so that anyone can comment it. So it must be public and somehow made that anyone with the link can comment it. The easiest way is to use the Google Docs. Share it such that anyone with the link can comment. But there are also some other, I think even on the Microsoft, what is it? OneDrive, you can put the Word document there, or share a Word document there, such that, well, at least I can comment it. So that's my feedback channel. But I actually myself I kind of use the Google things all the time. So those are, they don't have too much of properties. So it means that they work anywhere. Anywhere. Yeah. One thing, actually, these exercise sheets, read them really carefully. Also, that kind of stuff. They're all programs, files of your own must be documented appropriately. For example, easy way of missing some points is that you just have the code without any comments. At least one point out from because of that. At least. So there must be enough of comments. The minimum requirement is there. Okay, another one. Descriptive names for all the pins and such, all of the modules what you're using, all the variable names, descriptive names, not X, Y, Z, I, J, K, but something what describes the name already described where that where this variable is used. Okay, and then zip the project files and put it on favorite data repository. Okay, so but you can read probably. If you cannot read, and then you're beyond help now. Okay, when you have everything done, then just click the return form, which is just like that. Again, email address, name, which exercise, then link to the report and link to the main.c. Okay, to also have the click that one, and you will get the return received on your own records. All right, and so today we go through the fundamentals. Then the next part is the timers. Actually, I might go through the timers also today to kind of speed up the process. Then the third topic is data acquisition. Yeah. Then serial interfaces. Then we have SPI and I2C bus, which are also serial interfaces, but I kind of I noticed that I have very heavy exercise for serial interfaces, so I took a couple of parts out and put them separately on the SPI. And then, okay, this is just the intensive week now. We also have a project. Yoo-hoo. And I found out excellent topic for a project. At least I think it's excellent, actually. So it has some measurements and it also has some control. And now it's very popular to be green, which is a good thing for your sake and your children's sake. Yeah, seriously, we are running out of resources. Oil, we shouldn't use oil for burning. No, it's waste of oil. We use just to lubricate things and run everything on electricity and maybe produced by sun. Sun or wind, they are just good. Or then grow some stuff and use alcohol for burning. But anyways, that was the green stuff. So the green part now is the sun tracker, meaning how to maximize the power from a solar cell. You just face it to the light source. Okay. And I was thinking about how about say mobile power station or something like that For example, there are plenty of these oil tankers, tankers or container ships kind of things that you could, in principle, use some of the power, not all of the power, of course, but use some solar cells to power up some of the parts of the ship or something like that, or a car. On the other hand, should we use private cars? Maybe this by sharing. Okay, but this is Germany. Of course, we will be using cars. Okay, but anyways, so Sun Tracker, and this is very open kind of project. So design a device which optimizes the solar panel efficiency on any location, northern, southern hemisphere. Well, in Finland, how to optimize the solar panel efficiency on winter time? You cover it. Since it's cold and dark, you can. The only thing that the winter can do for your solar panel is to destroy it. Okay, but Africa or Central Europe, you have sunlight here enough for at least for lighting. Yeah. Yes. Yes. Definitely there. So, but anyways, there are basically two kind of problems. One of course is the sun kind of goes in a sinusoid way like that, or circular motion. Sun doesn't go anywhere; it's there, and the Earth is rotating, and then it's also a tilted axis, which means the summer and winter. So this elevation angle is actually also changing. So most of those power stations have a static direction for the solar panels, because it would be very expensive to move them like that. Yeah, and you would add moving mechanical parts, which means also on the maintenance cost and such kind of thing. So for the cost reasons, these solar farms are static. Okay, but anyways, you can be now innovative and think of a, say, car-size moving platform, not necessarily a car. Boat, rowing boat. How to power up a rowing boat? Well, row it. That's the green thing. But if you have a sailboat and want to have some luxury there, like evening lights and that kind of things, then you wouldn't need some way of steering this solar panel to maximize the power. Okay, but anyways, there are some boundaries here. So one is that you must use this piece of one to power it up. Then another one, well, this is because we are actually this is the piece of course. The second one, you must have there a light sensor, at least one, okay, and at least two servos or other. Well, it doesn't need to be servo. If you find some another actuator to change, servo is just one technology on the actuators. But anyways, you need at least two of those. So basically, one to steer the sensor, light sensor. So you'll find where the sun is, and then you turn the power solar panel. Okay, and in addition to that, you may use any other sensor actuator you need. Remember, this is we cannot even say prototype here. It's more like proof of concept level design. It's up to you if you make it a real device. Well, it must be, say, proof of concept demonstration. But if you want to exploit that one financially and become a sound tracker tycoon somewhere, go ahead. Well done. Send me a postcard. Okay. Then about the report of the project, link to the piece of files as this far, but then the project report must be done as a web page. Have you done web pages? Okay, the easiest way of doing the web pages is to use Google Sites. I can show you at some point how to actually do it. I have done my web pages with Google Sites. I have tried also other ways. 10 years ago, I had my own web pages running on Metropolia service, and I made the only way I could do that time was to actually write the HTML code, which is painstaking. It never comes out as you wish. Okay, but Google makes everything easier. And by the way, I'm not paid by Google. Just it's quite the opposite. So Metropolis is paying Google for some Google services, the organizational services. Okay, so basically the project report should have on the web page project introduction, electronic schematics, block diagrams, link to component data sheets, and then video presentation of your demonstration. Yeah, that'll be fun. Have you done any videos? Do you have a mobile phone? That quality is enough. Oh yeah. What I have done, you mean this one, links to component data sheets? Okay. Do basically similar to my exercises. So actually, I usually just, let's see, for example, timers, serial. Okay. At least on that one I have. So on the exercise sheet, I have a link. So that is just a link. Yeah, it opens up the datasheet. Datasheets, Maxim integrated com and so on. So it's just a link to that datasheet. Yeah. And how did I actually do this one? This is just a Google document, nothing more. Okay. Good. Any questions about the course this far? Okay. Let's see. You have already enrolled, and we have those 5 topics that plus the project. Yes, you have a question? Okay, deadlines are basically so that each exercise has 1 week deadline, but not from the second exercise deadline will be 2 weeks from now. Third one will be 3 weeks from now. Okay, that way. So 1 week deadline for each of those. So exercise will be done in 5 weeks. Okay. Then the project, I think it will take about 2 weeks to do the project. But I will be fixing the deadlines to the website sometime this week. But in principle, this course takes 7 weeks from now. You can do it faster, but that's the deadline. Then there's also a scoreboard, online scoreboard. And okay, looks something like that right now. Sorry, it doesn't really show up well, but anyways, I just used the first name on that line. It doesn't have your student ID numbers. No, it doesn't have your last name. So I think this is okay for everyone. So you can see which point is yours. All right. So, um, by the way, if you have some, if this name you gave here is different from the name you have on the Frankfurt records, please, you know, give me the real name. But I think these are your also the official names there. They look like that. Okay, but anyways, so this is 5 credits course. Just about 3 out of those 5 credits come from the exercises, and the rest 2 will come from the project. And the weighting is accordingly. So first exercises are 10 points each, and the last one, the project, is 30 points maximum. Maximum total 80 points. Then you need at least 40% to pass the course. But you always shoot higher. You try the best grade possible. Yeah, it's very possible that you can do it. Just don't make much mistakes, since the highest grade percentage, when in Finnish scale, it's 90%. But I need to find out the exact percentage for 1, 1.3, 1.7, and such kind of things. So the scales are a little bit different. So in Finland we have the 0 is failed, and 5 is the best one. 1 is the passing grade, and you have the opposite. You have the 5 is the fail, and 4 is the pass, and 1 is the best. Okay, yeah. But I'll do the fixing of the grades. Okay. You will get also the Finnish Metropolia certificate of studies here. Okay, good. So that was the scoreboard. Good. So now I think it's time to, unless you have some other questions, if you don't, then it's time to start up the engines. Just a moment. Where's my mouse? And find the program PSOC Designer 5.3, 5.4, sorry. It should be on the computers. Okay. And you can download it from the Cypress website. Doesn't open? Is there some problems? When it opens, it should look more or less like that, except I have a blank on the Meet. You probably have something else. So did it open up right? Okay, good. So the PSOC Designer is a tool for PSOC 1. If you have, let's see, or PSOC 3, I think. Yeah. And PSOC Creator is for PSOC 4 and 5. The reason is that PSOC 4 and 5 don't have so big, so complex mixed signal system. They have more processing power, but less of this mess what we have in PSOC 1. All right. Anyways, the first thing to do is to check which processor is actually on this board. Just a moment, I think. Yeah. So looking at that board, and it's either 27 something, so you're looking at this chip here. That's the processor. And in my, there is a CY8C27443. Okay. If it's different, then you probably need to change it. But I think Robert Mikalik has already changed that one. You found it? So that one, yeah. And then you need you have younger eyes than I have. Oh.
Oh, okay. It's written now.
Yeah, it's written on the top of it. It's laser engraved, so it doesn't really. Yeah, just like that, and then read the text there. Yes. So we will be using the processor. CY8C27443, and then PVXI or whatever that is. Basically, plastic. Plastic dip. So the last letters are always the case. What case, what kind of a package is on, and basically the first two letters here tell the how many resources we have on the system, and this tells you about the amount of I/O. Okay, but there's also the selection tool. If you know what you need, then you can select the processor. But in this course, we are using 2744443. Good. So this is the view how the PSOC designer shows up on the first time every time you start it, it shows this display. Just a moment. Okay, now I think it fits a little bit better on that. There, better. On the top left corner, those are the latest projects what you have created. Okay. Then there are some shortcuts down here. For example, how to create your first project. So they are actually quite nice selection of all sorts of self-learning material too. So yeah, use those if you feel like it. Yeah. At the middle, there's something. In my case, I have actually canceled everything. Oh, is it blank also to you? Excellent. Good. Maybe that's on. Usually, actually, it gets the PSOC, the PSOC community links, news, and such kind of things. I have a feeling that there's a firewall setting somewhere on the Cypress campus, or Cypress has kind of reducing the amount of those news right now. Yeah. Oh, excellent. Yeah. So no news. No news is good news. But anyways, this is something you also should take seriously. This design support, related documentation. So application notes. So if you have an application like a solar tracker, it would be nice. You probably can find some examples related to that one going to application notes. So for example, how to run the PWMs and that kind of stuff. Yes, you have a question. No. As long as it fits on the fits there, it'll be fine. Okay. code examples, well, a couple of those, design guides, how to, basically, those are more like the design styles and that kind of things, I think. There are actually 66 different development kits available on Piece of Work for different processors, for different applications. Like they have the design kit for USB PSOCs and some other. They have their own wireless communication kit also. They have Bluetooth low energy kit available. So if you get into this Cypress PSOC kind of word, then you might actually also find those very interesting. And other resources. And there are blogs and press releases, webinars. So if you don't have any, if you have a life, then you can you start going on that community, and then you don't have any life anymore. Okay. All right. But anyways, let's make our own first project from scratch. So on the left corner, there's a new project, or actually, I think you can also make it from under File, click the new project. Okay. It's good to read what is there. Usually, you just click OK, 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 OK. And that's how I install programs. Are you certain? Sure, you want to, destroy everything to your hard drive? Yes. Oops. That's why you take backup copies. All right. So, name of the project. What did I tell you about the descriptive names? It starts here. So, PD project 6 doesn't tell anything to anyone, so I might actually put here PSOC exercise 1 and then my initials. For example, like that. So then it's descriptive. Use your own initials, not mine. All right. Workspace names, yep. Create directory for workspace, that's good. And project creation, you can either start from new project or clone existing projects. It's your own project that you want to just continue. So this is actually good for the basically if you have a working design, continue by making a clone of that and add some more features. So in some case, quite often you end up having some sort of a mind block and it doesn't work anymore. It can happen a lot of times. I will tell you stories later on. But anyways, then there's a clone example project. So if an example project actually is available on that application area, if you would like to make your project, that's also one good way to start. That's why Cypress have hired some engineers to build these example projects. Good. So, but we start from the new one. Target device. This device here should match your physical device, at least on this level. This doesn't give much of any information how this looks inside and how many pins it has outside. This is just a packaging. The chip is that one. So at least the first part should match exactly. Otherwise, you cannot program it. That'll be disappointing. Anyhow, you can always also go to the device catalog. Okay, so the device catalog has all Cypress piece of circuits available. The gray ones here, they are not recommended for new designs anymore. But if you have a stock of old processors, you need to dispose somehow. Well, that's up to you. So, for example, I think you can find old stocks of processors from Alibaba or eBay or the wishlist or something like that on an internet. So, and they're usually quite cheap. So for home projects, those are usually just fine. Not for your company's projects though. Anyhow, okay, as you can see, the parameters you can check also. Pin count. Pin count is the first parameter, and you can actually just take, devices which have 20 pins. And then you can actually start, which are available on DIP packages. Yeah, not too many anymore. Let's see. Like that. And then actually analog blocks. How many analog blocks it has? There are some devices which don't have any analog blocks. But I think those usually have something else. I have no idea what those are, though. Then how many digital blocks? Okay. So maximum number of analog blocks is 12, and the maximum number of digital blocks is 16. I think. This is why I started using piezo processors. Capacitive sensing, direct capacitive sensing with single microcontroller 10 years ago. Or more than 10 years ago, 2006. And that time it was really no external components. But now they actually have changed that design so that you need one resistor and one capacitor externally. With the old piezo designer, you can still do those designs without the external components, but I think one resistor and one capacitor is not too much to ask for direct capacitive sensing. My problem or challenge was to find a way to figure out when a lure is in water. I do a lot of fishing. That's my favorite hobby. Okay. And I made my first wooden lure when I was something like 10 years old. And the basic fundamental is very simple. It's made of wood. It looks a little bit like a small fish. It has a wire inside. So this part will be attached to the line. And on the other end, you have the hook. Like that. There might be also some, extra hooks here. And how to make it actually look like a lure on the water for the fish. You put a plate here to cause some turbulence, and this one starts, if you look it on the top side, it starts actually wobbling when you start pulling it. It's basically causing a chaotic, not chaotic, it's more like an oscillation. So it turns one side and another one, and like that. So predatory fish thinks that it's a small fish. I wanted to add some electronics on it. Why? Beats me. I just wanted it. I didn't need it. I wanted it. Uh, so basically, there at that time, 10 years ago, there already was some electronic lures which has say blinking LED lights on it and a battery. The problem is that those two problems actually with those was that they had a bottom battery, the lithium bottom or silver oxide battery, and basically it was replaceable. And if you have anything that opens on system which is submerged, you will start leaking. It will start leaking at some point. So, all right, I didn't want to do that. So what I then actually wanted to have is to have a rechargeable battery inside, lithium polymer, and the charging of it basically, this is metal, this is metal. I just cut that metal and charge it so that there's +5 and 0. Not a big deal. Anyone can do it. And this can be actually put into epoxy so it stays dry, guaranteed. And then, of course, you need the electronics, which is not a problem. Oops. So electronic is not a problem. So you have just a small circuit board there with the microcontroller, any microcontroller. The first version actually had an 8051 type processor, so the 20-pin version, 2051. Another issue now, how you turn it on and off. There are several kind of things. It can be just a magnetic switch. That was the first version. Then I wanted more. I wanted this one to turn off only when it's on water. When it's on dry land, it doesn't need to operate. But when it's submerged, it should start operating. So what I did actually was to make the circuit board going all the way. Well, this way I can actually directly attach these wires on the circuit board. I don't need to do any extra soldering. Then another thing, I could cut it like that. It doesn't affect on the how it's actually what's doing there. So, but looking on the top side, I have a capacitive sensing area here. So it's fundamentally it's just an like antenna. Okay. And what happens when you put this one on water? The surrounding material changes, and which means that the capacitance changes. So you're changing the permeability of this sensor. And okay, now I have a problem how to sense the capacitance. And I found out that this direct cap sense actually works just fine. Then I also found some use in education. Okay. Yeah. Another property is flash, amount of flash memory, meaning programmable read-only memory. Maximum 32 kilobytes, which means, well, it's half of the full address scale in any case. So it's enough. Enough for 8-bit processor. Read random access memory. Okay, maximum 1K. But there are also smaller processors with much less RAM. Which, well, that 1K or, well, few hundred bytes is usually enough for RAM. On embedded systems, in any case, you should recycle the RAM locations as much as you can. Um, no, 256. Yeah, it says 256. No, 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 no. Wait a minute, wait a minute. That's where's my 20? Yeah, it looks like it does that. Part number CY8C27. Where's that 27443 has there? Okay, 16K of flash, 256 bytes of RAM. That's enough for, say, 8-bit applications. And actually, you can also use that flash for temporary space. So there's also a kind of the EEPROM simulator or emulator. So you can define part of that program memory as a normal data memory, non-volatile data memory. Okay, I/O count 24, which is quite nice for 28-bit pin chip. So there are only 4 pins which cannot be used as I/O. So positive and negative power supply, of course. Then it has the SMP, which is the charge pump, and then reset pin. This device has a external reset also. Not all the devices have the external reset. Power supply range from 3.0 to 5.25. Well, that's nice. Although this can range on 1.75 to 5.5. It's actually the highest ones, and but anyways, with this SMP, you can run this processor from a single cell, 1.2 volts actually, or less than that. It's 0.8 volts is the lowest battery voltage. It's the charge pump still works. USB interface. This device doesn't have it, but there are some devices that has full speed USB interface, 2.0, not 3.0, but 2.0 compatible the device. Wireless interface. Okay, there are some wireless interface devices, meaning that it has it has a hardware for radio and software and blocks to actually do the protocols and such kind of things. Temperature ranges, well, minus 40 to 85 is, I think, it's still. And there are some devices, Internet for Automotive, which go higher on the temperature. All right, so legacy means dinosaurs rode the earth. Okay, don't use those. So on legacy, it should say no, not legacy yet. All right, so, but I'm happy with that 73443, 24PXI or SXI, whatever I. Okay, click. There's also selection if you use C programming or assembly. I highly recommend using C programming. I'm not that old, you know. I don't see. I have been lucky with the, digitalization. I'm the generation who started the using the mainframe, but I was on the university on the first year when we started to have the workstations, and those were still, different kind of workstations as these here, big, bulky, and then we also started getting PC, AT, XT. You may have heard those from your grandparents. Now what we now call a PC is actually a upscale version of AT. And then we have one single core of 386. I started the first computer has 186. Nokia Micromicro was the fastest PC on the earth when it came out, because they started using some mid version of 86 kind of processors. But anyways, that's bygone, old. That's ancient history. Anyhow, now we have a computer which has more computing power than those big mainframe computers at that time. Or actually, my mobile phone has more computing power. Okay, this is back to the basics. Doesn't have too much of power, but there are plenty of applications you really, really don't want to have that much power. Don't overkill it. Okay. Anyhow, now you probably have this kind of display there, right? So on the left top corner are global resources, which you can change. For example, now my CPU clock is 3 megahertz, which is basically system clock divided by 8. That's just fine. We can leave it like that. But if you need faster processing speed, you can actually run it to 24 megahertz directly from the system clock. So if you need a processing speed. On the other hand, I have found that, for example, the LCD does not anymore work with that setting, because this one uses software. Software module, software driver. So it's such a subroutine package. And if you speed up the processing speed, you might actually start writing too fast for this one to process. These are the standard Hitachi C. It's 20 by 2 digit LCDs. The original design is from 70s. For that, you know, as long as we have had LCDs, Hitachi was the first one to actually have a decent electronic circuit to actually handle the LCD displays. I think it's probably, I would say, the bigger chip here. So it's a dice directly on the on our printed circuit board, and then wires, and then some protective coating. Okay. So the CPU clock 3 megahertz is just fine. If you are in a very low power design, then you would let that clock run as fast as possible. So the processing time would be shorter. So the processor actually will go sleeping more. Okay. 30K clock, meaning 32,000 and so in 2 to the power of something. Is it 15? Clock source. So you can actually have an external clock source to make this as real-time clock. So that 32K clock is actually the clock for the this digital watches. Phase lock loop. You can actually run some of the these functions with a double clock rate. So there's a phase lock loop to provide 48 megahertz clock for some of the modules, some of the digital modules. You cannot run over speed the CPU though. Okay, sleep timer. Okay, so this processor has a built-in sleep timer. I think ABR also has a sleep timer, right? Maybe. But anyways, this one has. So you can actually put the processor to sleep, and then it wakes up for example, on a pin interrupt. That saves some power. Good for battery operations. And sleep timer is also the easiest way of doing the timing of your software. There are 4 settings for it, so you can run the sleep timer at 1 Hz, 8, 64, or for 515 Hz clock rate. And this is roughly 1 Hz, not exactly. So not good enough for the making a real time clock. Okay, more resources. We have the system clock, the dividers, VC1, 2, and 3. VC1 is actually a divider for this 24 megahertz clock. So it's always system clock divided by n, and this is the n, currently 60. Then VC2 is always a divider for the VC1. So basically, those are both 4-bit dividers and cascaded like that. Then there's this VC3, where you can select the source of it. So it's either sys clock, a VC1, VC2, or system clock times 2. Okay, meaning you have to turn on the PLL to have the 48, but then you can actually use this one to divide it. For example, how to make 24 megahertz divided by 3. Well, you double it with a phase lock loop and then divide. System clock divided by 1.5 was something I was thinking about. So how to divide by 1.5? Well, first you first you multiply with 2 and then divide by 3. Yeah. Okay, and this is 8-bit divider. System clock source. You can also run this chip with an external oscillator. I don't see the real reason why you would do that, since this 24 megahertz clock is, just accurate enough for the processor, and you cannot overclock the CPU core in any case. All right. System clock by 2 disabled. Analog power. Okay, you can actually control the power consumption of the circuit, and this is one of those settings. You can turn all the analog power off, meaning that if you are setting the system to sleep state and you are using analog systems, the analog usually take more power than the digital devices. That's just it comes from the physics. When you have continuous time amplifier, yes, it consumes power all the time. Just because. But for the sleep time, you can turn analog power off. Then at the sleep, you can then turn it on again. Just a small reminder that it also requires a little bit of time of settling time when you have to turn it on and off. But it saves energy. Okay, we will actually go through this again on the data acquisition part, but on the reference multiplexer, that selects the analog signal range of the analog parts. So you can actually run it a reference to the power voltage divided by 2 plus minus band gap, or you can actually, there's different ways, but anyways, I think the most common way would be to have 1.6 times band gap plus minus 1.6 times band gap. That means that if you would make an A to D converter, it means something. Otherwise, you should never trust the power supply voltage. Never trust that one. So use only band gap voltages if you want to have good analog to digital conversion results. So always the band gap reference. Analog ground bypass. We'll go through that again. Op amp bias. Okay, low or high. Analog buffer power, low or high. Okay, switch mode. Switch mode pump actually is the pump to step up the voltage. It requires a couple of external components. Step up regulation needs the 3 components for that kind of devices. Capacitor as a charge bank, then you need the inductor, and then you need the usually the diode also, but the switch. So yes, capacitor for charge bank, inductor to make the current going, and then switch to switch it, and then the diode to prevent losing of the power from the capacitor. Okay. This has a low voltage detection, so you can set where the low voltage detector actually turns on. So this one makes the low voltage interrupt, which causes halt almost in any case. You can actually also make your own code to prevent halting and browning out the circuit. Okay. And there's a low voltage throttle back, something like that. And supply voltage actually either 3.3 volts or 5 volts for this device. And we're using 5 volts because this one gives 5 volts. On the lithium powered system, you would put there the 3.3. And that voltage, of course, it doesn't need to be exact. It just sets the some parameters for those for the system, so it's optimized for that range operation. So there's quite a big tolerance on the supply power. Okay, watchdog. Are you familiar with the watchdog? Okay, so if you get a watchdog, it barks, right? If it stops barking, then something is wrong. Okay. And in this case, actually, it goes that you have to go and feed once in a while your watchdog. Meaning you need to visit the watchdog routine. You need to clear it in software. So in case there is something going wrong on your code, it would mean that okay, you haven't been feeding that watchdog for a while. And then the watchdog actually takes over and eats you. So it goes and resets the circuit. Okay, so that's one of those important things when you have a, say, any mission critical application, meaning if you have a say, health technology instrument or something like that, it must run or go blank. So it cannot do any mistakes on the running. That's where you use watchdog. All right. So I would guess that there are these self-driving cars now making accidents. I'm just guessing they don't have watchdogs on the system. Haha. Okay. Yeah, that was the left corner, which means that all of those are used. Those are the common global resources for the processor. Okay, pinout. Different views of pinout. On the lower left corner, you have full access to all the properties of each pin here. You can rename the pin. You can select which kind of drive it has or where it's connected. Standard CPU means it's controlled by the CPU itself. It can be also sent to analog input, global in even 0, okay. So basically it can be used as an input to those green lines here on the left, or output to these green lines. But the standard CPU is fine for now. Drive. Okay, that's a little bit different from processor to processor. Usually, most of the processors actually you can turn the output drive either to strong or pull up or high Z. In PSOC, there's a little bit more selection. By default, this is defined high Z analog, so well, at least the port 0. Port 0 can be used for analog input. Okay, and which means by default is high Z analog, so you can directly use this one as a analog input. You can set it to digital high Z also. Then it's basically not connected anywhere. Then open drain high or open drain low, meaning that which side of the transistors can be switched on or off. Pull down. Pull down basically means that you can draw current, but it cannot be used as a source. Pull up, the opposite. Then there's a strong, meaning it can be as a digital output, and then the strong slow means that the rise time is slow, meaning that if you have a long lines, then it doesn't do the oscillation on those lines. Okay, so quite say a flexible way of defining the output. Okay, and of course, interrupts. So all the pins can be also defined as interrupting pin, either falling edge, rising edge, or change from read operation. So it's just a change. Okay. Initial value, okay, it's either 0 or 1, meaning if you have an output, does it start from value of 1 or 0? A big difference when you are basically having, for example, the low active lines, if you are driving low active lines. Okay, so all the pins actually can be set up here. You can actually do the same thing by clicking the pin right there. Okay. Or let's see, if you double click the pin out, you can do also the definitions here, I think. Yeah. That's actually nice, and this is why I want also you to, when you're doing a some external connections, you also rename the pins according, since it's directly the pin out of your chip. All right, so we haven't done much of anything yet. Just went through the surroundings. Okay, the part of the switch matrix is shown here. So basically, those are the lines for output, which can be connected to the pins, and these were the input lines, which can be connected to any input pin. Then we have these rows, row kind of thing. So row 0, input 0, which is currently connected global input even 0. Okay. How about if we want to actually connect global in odd 0, meaning that actually we have a pin port 1.0 connected first to that line, and we want to route this pin to that row. Well, this is actually just a multiplexer. No. So we can actually connect global in odd 4, odd 0. There. So that's how you make connections. These lines are actually organized as nibbles, half of a byte. 4 lines only. And then the even number ports and odd number ports actually have different lines. Okay, and only pins of 0 or of 4 can be connected to, wait a minute, not pins. Only line 0 or 4 can be connected to those row 0 line, horizontal line. Okay, so there are some restrictions how you can actually do the connections. Yeah, I will show you. So basically, let me see. Yeah, and again. All right, so let's think that we have a signal on coming to, well, I'll take another port here, port 1.2. That will be my input. Oops. Input from somewhere. Input X. Okay. 1.0. That 1.2 can be connected only to, this is an odd number port. Port 1 is odd number. Port 0 and 2 are even numbers, and port 1, 3, 5, 7 are odd numbered ports, which means that we can connect this pin to global in odd 2. There. Now it's connected to this line. How to connect this line to then vertical row or row input? On this row, we also have the multiplexer. And you can there select that global in odd 2 line to this row. There. So there are some restrictions on how you can connect anything here. Yeah. It depends on the port and pin. Yes. Okay. Yeah, that's fine. Okay, and then click that one, and then you go to port Oh, that's global in odd 2 here. Left a bit.
Okay.
There. Next one. There. Click.
Okay. Okay. How do we confirm those pins?
Well, do one by one, one at a time. So first you need to connect this pin to this one. Click pin.
Pin.
Mhm. Yep. Select port 1.2. Okay.
Mm-hmm.
And now you can actually select the row in odd 2 down there. Click that one and no. Uh, just click and then the multiplexer. Global in odd 2, GIO2. Oh, close. Ta-da! Now it's on the same line. Okay, got it? Good. So that's how you route a signal. Hmm? No, that can be then connected to any of these blocks as input. Yeah, but we don't have any functions there, so it doesn't connect yet. Well, that'll come later. Let's go first to the routing of the signal. Okay, then the block. The block outputs can be uh, connected to this row outputs, row 0 output 0, which can be then connected to pins 0 or 4 on any port. Okay, 0 goes to 0 or 4, or 1 goes to 1, pin 1 or 5. Okay, the same way. So, for example, if we have an output here going to, and we want it to pin 1.1 is not used, so we can connect pin 1.1 only to this, and pin 1.1 actually goes okay, output X. And let's see, let's let's make this one this output so it's strong. And then that can be connected only to, so this 1.1, so it's odd port, and yeah, 1, yes, global out odd 1 to pin 1.1, okay, and that can be connected into row 0, 1. By the way, this multiplexer is kind of nice. You can connect the same signal up to 4 different pins if needed. There. The only problem that we don't have any function on the on that any of those blocks yet, but that'll come later. So this way you can connect anything basically to any pin. It gives a lot of flexibility. Also, I agree this is quite complex kind of way to handle. The analog blocks down below, there are a little bit more restrictions there, but I will go through the analog sections when we have the exercises on the analog blocks. Okay, so let's do some functions. All right, so this is the set of predefined user modules. Actually, you can find probably everything from here. Well, if you get into advanced level, then there you can also build your own custom user modules, but that'll be you know 2 years from now. Okay. Yeah. So we have user modules for A to D conversion, amplifiers, analog communication. What? Analog communication. DTMF, practically. Dual tone, multiple frequency. The old dial tone. Dee, 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 dee. That one. Yeah. Counters. That's nice. We have counters. And let me just open it. So we have actually from 8 to 32-bit counters. You can actually do quite a lot of with those. And say, just for example, if I take counter 8, double click that one to add it on my design, it takes one of those blocks. So each of the digital block is actually 8 bits. So if I wanted to counter 24, it would take 3 blocks. Okay. On the other hand, you can always, if you need a lot of counters, you can take 30 or a very long counter. You can actually start it from the up row and then connect it to the bottom row. They are routing kind of things. Those digital block inputs and outputs can be connected to almost any input or output of those digital blocks. Okay. So yeah, you can make 64-bit counter. I don't know where you would use that, but you can do it. Oh, cascaded counter. Okay, D2A, mixed signal. So this has a digital to analog conversion up to 9 bits only. Then digital communication. These are mostly hardware blocks. So there's a cyclic redundant check for 16-bit data, for example. DMX5, I have no idea what is that one. There's easy I2C, meaning you can actually make a piece of circuit that functions as a I2C device. Then there's a hardware I2C block, meaning that you don't need more software resources. It just have the read and write operations for that hardware module. Save some computing power. Then it's I2C master. So this actually can be used to read and write or control the I2C devices. One way to use basically if you have multiple controller system, you have one as an I2C master and the other ones as a slave. So the master would be controlling all of the other processing devices. Okay, infrared data. A standard IRDA, both receiver and transmitter. MBM, I have no idea what is that. One wire. One wire sensors. Those are probably the most used temperature sensors in the world, since you need only 2 wires on one wire. Of course, you need, you need the data, which can be also the power, but you need always the ground. But one wire is a trademark. Receive 8, so it's a standard 8-bit asynchronous receiver. SM bus. SM bus is actually one. It's the extension of I2C. It's either I2C2 or SPI extension. SPI extension, yeah, okay. SPI master. Okay, that's nice. You can have plenty of these SPI devices there. Oh, that was SPI slave, basically. The SM bus slave is SPI slave. Okay. SPI slave by itself. Okay. Wow. 8-bit transmitter. That's the easiest way of debugging without the LCD. You basically just run this transmitter, and then you have a serial port on your computer and just run the signal there. That's the easiest way without the LCD, of course. I'm using it on my lure. And then there's a transmit with software. So if you don't have enough of these hardware resources anymore, then you can actually use the software module. Yeah, and that's the hardware software trade-off you need to think of there. Then a full WART, universal asynchronous receive transmit circuit, which does everything too. Okay, so those are very nice set of digital communication. Filters. Okay, bandpass filters or low pass filters. Analog, switch capacitor analog filters. Then some generic stuff like a switch capacitor configurator or switch capacitor block kind of things. Okay, LED dimming, yeah, sure, why not? Some legacy which you shouldn't use. Yeah. Okay, this is the most used blocks actually. LCD. Direct software. The software module should run LCD device directly from port 2, or well, in this case, it's actually connected on a port 2. LED. How to make blinking LED lights. 7-segment LED. Good. One shot. Pulse width detector. Not just you can do the pulse width modulation, but also this can be used for pulse width detector. For example, these ultrasonic rangefinders the pulse width is the measuring, giving the range. So you could use the pulse width detector to actually have the measure of that one. Okay, shadow registers. Are you familiar with shadow registers? Okay, that's a good trick if you want to, for example, inverse a LED. And the LED, for some reason, doesn't have big enough the resistor there. For example, you want to run it at the full tilt what the processor gives, but anyways, it might be that you don't get the output voltage of that pin high enough to be logic state 1. Okay. So if you use just the invert that pin, you need actually shadow registers, since you cannot just read the pin and rely that it's the logic value is 1, although you have been writing the 1 there. So those are different. They can be different, and they most certainly will be different. So by using shadow register, you will write always the value what you want on that volatile kind of register. You write your value there and modify it, and then write the shadow register value to the real register value. So shadow is just a basically your wish what the content should be. Okay. Serial LCD and sleep timer. Okay, for this exercise, first exercise, you actually need LCD, LED, sleep timer. Just double click those. Okay, let's go. I'll just open some of those. So multiplexers, we actually have the multiplexers for signal are right here. So 4-bit multiplexer, and then basically making an 8-bit multiplexer means that there's also a these can be selected using 2-bit multiplexer here. So 8-bit multiplexer AMUX is either that one port 1 or then port wait a minute. So this is the odd numbers and even numbers pins. Okay, yeah. Same thing for those. So either 4-bit multiplexers or 8-bit multiplexers, and basically you can have two 8-bit multiplexers, or I think you can have also you can have up to 2 4-bit multiplexers. Does it go like that? Maybe. And then reference multiplexer, the internal references, where to select the analog references. Power management, you can actually have a voltage sequencer there, meaning that you can give some certain predefined level voltages also out to the circuit. It basically uses a D2A block to do that. Protocols, okay. You can actually boot it from the I2C EEPROM. Okay, PWM. For servo control, for example, you need PWM. Pseudo-random numbers. Quite useful if you don't want noise. Or if you want to run a, say, spread spectrum kind of things on radio frequency. Okay, that's the RF is basically just easy to use module to connect the Cypress RF circuits as a coprocessor for that one. Temperature, okay. 2 sorts of blocks. Flash temperature, so there's a temperature sensor right on the top of flash because it doesn't tolerate too high temperatures. That's one reason, and also you can use that one actually as a some sort of indication of how hot the device is. Thermistor, that's a special block to connect certain type of thermistors directly to this device. Thermal management. Yeah, fan controller there, and then 5 different timers, 8 to 32-bit standard timers. Okay, and then tachometer timer. Tachometer is used for timing of the ignition on cars, for example. Okay, good. So those are the modules. And we already put their counter 8. We are not using it on this exercise. We can always delete it. And of course, it asks if are you sure? Okay. Then let's take a quick look how to actually uh, configure these modules. Now we have LCD_1. Good idea is to change the name so that it means something. For me, there can be only number one if there's also a number two. That's one of the rules of making, papers. If you have chapter 1, you must have chapter 2. If you have chapter 1.1, you also have chapter 1.2. So, okay. I have only one LCD. Okay, that's a good name for LCD. And on this board, we are using port 2. Okay, bar graph, enable or disable. If you are not using bar graph, meaning, those, bar graphs, bars, then basically disable it. It saves a little bit of the flash memory space. Nothing more. I think it's was it 400 bytes of memory or something like that? I don't remember exactly. But anyways, it saves some space. And again, if you are not using, why you should have it there. And okay, you can actually change those values also on software if needed. I think. How to use this device or function? Well, on the right corner, maybe also on your computer, there's actually this kind of hidden datasheet view. So the current datasheet always shows up on the datasheet view window. Absolutely wonderful datasheet. So it tells you everything what you need to know about the how to do the connections. For example, well, if you want to make your own circuit board, then that's the pin out for connecting the LCD there. Okay. And if you do your own design, then it doesn't need to be port 2 anymore. And the nice thing about this device environment, if you basically made your testing with the circuit board like that, and then on the final design you have, for example, port 0 as your LCD port, you just click it on your design and do the compilation like that. But right now we have the port 2 as the LCD port. You can also use port 1, but I already defined some pins there as input or output. Then basically they were reserved. Actually, port 2.7 you can still use as a digital output. Okay. Let's go to the data sheet. How to read this one? Well, there's plenty of information. For example, here, okay. So bar graph disabled uses 434 bytes of flash. Okay, so it actually also shows you the available resources and that kind of things. It does not use any blocks. It's a software module. Okay, and yeah, it uses that industry standard Hitachi LCD display driver. Functional description. So how does it actually work? Well, that's how. Placement, meaning where you can actually place this one. So basically requirement is only that you have 7 pins of one port. And parameters and resources are actually referencing these parameters in here, nothing more. It explains those. If you are not sure about what the parameter means, then open the data sheet and look under the parameters and resources. It explains each of those lines. Then application programming interface. So that's pre-written code available for you. Isn't that nice? It's like a software package what you download from some weird resource without no guarantee that it will work. These work as long as you follow the instructions how to use them. Yeah. Okay. So each function actually has the kind of start and stop the function. So LCD start initializes LCD to use the multi-line 4-bit interface, and this function should be called before all other LCD functions. So if you put this one, then you need to add also LCD start on your code. All right. Then the functional kind of things, position. So you can put the cursor on certain place on the LCD. So the first row is 0, or the top row is row 0, and the second row is row 1. Okay. And then also the column, it starts from 0. The first point here, first element here is the 0, 0 on the top left corner. All right. Then a couple of nice functions. You can print string or constant string. What is the difference between a string and a constant string? So variable string is actually something that you can change. It's on RAM, and constant string is on ROM. You cannot change it. And since the flash and RAM memory are on different address space, you have to tell to the subroutine where to get that code, or where to get that string. That's why there are 2 of those. This is quite popular on this. Let's see, this is Harvard architecture, or the other one, the microcontrollers, which has the separate program and the data, the memory at the space. Was it Harvard? I don't remember. Yeah. But anyways, how they actually differ on code is explained here. So if you define a variable, so this is a string variable which is initialized as user module. It actually points on a RAM space, and this is just the address mnemonic is that str. And compared to this direct printing of a string, that will be constant string, since there is no reference to any variable of that constant. Or if you put define str constant string, that will be then defined as a string on ROM. Okay, and that's accordingly you would use the C string or just PR string. Couple of other nice things. This is the fast way of doing showing some numbers. Is the hexadecimal. That's the natural kind of geek style. Geek natural. Or well, that's 8 bits byte or then 16-bit integer PR hex int. If you want decimal numbers, you actually need to do either I to A, integer to to string, ASCII, or then you can also use the printf with this part of stdio, or the .h, well, stdio subroutine package library. So yeah, printf, or it's actually formally it's printf, is printing to a string variable. It's formatted, but anyways, it takes, say, it takes some code space though. But well, if you need to do it, then you just need to do. Yeah, then bar graph functions also. We'll just go through that one, so you can make a nice bar graph out of it. You can also do all sorts of graphical operations to, if you tweak a little bit of this LCD module. One of my say multiform students a few years back made a Tetris. Used a 20 by 4 LCD and piece of circuit to make a Tetris there. Yeah, big respect. And some optional functionals like LCD control or LCD write data. So you can actually control that Hitachi circuit. So if there's some property on that Hitachi circuit you want to utilize, yeah, it has the software to do it. And some delays. In some cases, actually, you need to put some delay between, writing stuff to let the process to work. And this is the best part. Well, that's IKEA kind of coding. Needs some assembly. But sample project written in C, and you just copy and paste that one and run it. We can do it. Yes. We have everything what is required to run this one. So we have this block. It's called LCD. It's on port 2, bar graph disabled. Works fine. About the naming convention here. All the functions, rewritten functions, start with the name which shows up in there on the real design. If you want to call this LC like C3PO or R2D2, you can do it. Or Luke. Use the Force, Luke. Yeah, you can do it, but then you need to also edit the code. So that R2D2 module would be that one here and then underscore. All right, so let's go to another view now. To get there, you first need to do clicking of that top button there. It says generate configuration files. So after we have done the editing of this hardware, we need to tell the uh, system to generate also the software accordingly. It doesn't do it, while we are doing. So this is done by engineers for engineers. Okay, so click that one. It usually also gives you some warnings, like in this case, level 1 warning, currently power on reset voltage is set to 2.9 volts. To change the power on reset, the VLTCR should be modified in main code. Well, we have 5 volts flat done. This is not battery operated. We don't need to worry about the warning. But anytime when you have warning, figure out what is the reason, and is this really a warning, or is it a error to happen later on. Good. And the code. Where is the code? Where is the code? Click that one. So the code is under that one. Piece of exercise 1, Antti KP. There's a library files, external headers, such kind of things. There's a boot table, flash security kind of thing. Okay, flash security is about which part of this flash is used for program and which part is used for the EEPROM, for example. So you have software access also to that flash, but not to the code. You cannot actually do, well, you can, but you have to do quite a lot of work to change the code from the processor. So they try to prevent doing accidental damage to the code. All right, so source files. Those are the source files which were generated when I clicked the button. The boot.asm, okay, that's the boot code. When you turn on the power on the processor, it starts that file, which means it does actually, inside of that boot, it does basically initialization of the processor, meaning it changes the register values that are controlling the global resources. And if you actually set up the, for example, here, the port 1.1 drive, it's defined here, and it's part of the boot code. So this tool is just a design tool to do the most of that ugly stuff automatically. When I started doing my first microprocessor code, I had to actually initialize the processor, writing the assembly code there first. You don't want to do that, believe me. So, and the last line on boot.asm is actually to call the main routine, which is written in C. Double clicking, you can start editing. Can I actually make this one bit bigger? Yes, I can. Yes, I can. You can start editing it there. Yeah, so that's generated by the SOC designer. And the first thing what you should do is to claim that file to yourself. So what it is, SOC course exercise. One. You're familiar with C programming language, right? Yeah. You thought that a little. Yeah, yeah, yeah. Well, we need only the fundamentals, like uh yeah, what is how to start the comment and how to call, yeah, and then basically the syntax. If you are familiar with the syntax, you will be fine on this course. We are not making big numbers of lines there, hopefully. And then basic, there's some fundamentals how to write good code. One is encapsulate, meaning if you have some blocks that belong together, keep those together. And if those blocks are code blocks are getting long enough, make a function to encapsulate it. So the worst of codes what I have ever seen are just a linear code, only one function called main, which has everything on it. It works, but if you have one more small mistake somewhere, how you can actually find it? Okay. And then another one is comments. Comments. And in this case, also the author. Okay, and then, uncomment this line to enable global interrupts. If a module actually requires to use of the global interrupts, then you just, remove those couple of things. Easy. But now we should actually try the LCD code, and code sample is right here. Just to test. Copy paste. I hope that you know how to do copy paste, right? Copy paste is the invention of my generation. All right, you can freely use it. Okay, but anyways, another thing also that looks ugly, right? You should also use some indentation there. So yeah, so my favorite way is actually just remove those and replace it with tabulator. Make the code look nice and tidy. It's easier to read that way. Okay. Good. So next step would be to compile. But on the other hand, my favorite place is to just click the generate build. So it actually generates all the files over again, and this also builds that one. So it doesn't hurt to do the generation. These are fast computers. This is not the computer what your grandfather used. All right, and it does do some output. Oh, wow! 0 errors, 0 warnings. At least the code is okay. And now, what we need to do on the hardware, connect the LCD. There's the connector for it. Make sure that it lines right. It's easy to make one pin offset, then it doesn't work anymore. So something like that. Then you would need the programmer. C. Mini USB. Wow. And you know what to do with the other end. If this is the first time you actually put that programmer on the computer, then it starts downloading the drivers and such. So it takes a couple of minutes. But in this case, I have used these devices already quite plenty of times, so it already shows the green light. When that is ready, there's only one place you can stick it here. There's a connector, white connector on the bottom. Well, it's on that corner, close to the close to that those power pins. By the way, this development board can be also powered by the standard industrial 9 volts battery or external power source up to 36 volts. It has a standard linear voltage regulator too. Okay, so that one goes there. Yes, the right way. Done. Okay, so the programming, it's on the SOC designer and the program. Program path, Control F10. Click. All right. At this moment, actually, it can actually start updating the firmware of this programmer. All right. But anyways, you can have several programmers on the same system at the same time. So then sometimes if you have that kind of case, you can have actually several of these together when you are doing a bigger project, multiprocessor project. Okay. Then the acquire mode, meaning how do we are doing the programming of the chip. Reset mode is faster, and this device has the reset pin. Not all the devices have reset. There are actually 8-pin devices on PSOC which don't have the reset pin. So this power cycle is mostly for those. But any device which has a reset pin, use that one. Then verification. It slows down a little bit of the process, but I will say keep it off until the program doesn't work and you cannot find the reason from your code. So then you put the verification on to check if this device actually has something wrong with the flash. It happens. It's the electronics. All right. Power setting 5 volts. Since we are using reset mode, to program this one, you have to turn power on. So you get red light on both the board and also on this programmer, mini-prog. And then that button is the program. Program is starting. Done. And it's powered. And there's LCD. PSOC LCD shows up on the display. Okay. That's a lot of fun. You know, only a couple of function calls, and that's it. The same thing with all of the other devices. Okay. So, basically, I could leave you to work on the exercise to see how you can actually manage that. Just for fun. So, exercise. Where do I have my exercise? So in here, that's exercise 4. Exercise 1. What you need to do on the exercise 1, well, you have done more or less the task 1, follow the leader, fun game. And if you want to make your own notes, well, you make your own personal copy to your Google Drive. Then, okay, add a LED into your design. LED module connected to port 1.0, port 1 bit 0 meaning, and make the LED high active. So basically, there are these LEDs in here. They are disconnected. They have just the resistor on it, the current limit in resistor. And okay, I can show you. Then you need some wires. You have set of wires with the package probably, but there are also, if you need more wires, one of these boxes have a lot of wires. Yeah, more wires. I had a bunch of them on the. So, how the LED 1 actually works. You know, you can just check it like that one. Oh, wait a minute. Yeah. Ah, why it doesn't work? Yep, it works by connecting the wires. Your task is actually to connect port 1.0, which is on the corner there, and connect to any of those LEDs. I think it was LED 1, the physical LED 1. Was it that pin? And make the software so that this one blinks. So port 1.0 is right there, and connect that one to LED 1. Physical connection. Yes, your question. You have a problem. Are you sure that it's your problem?
It's
Failing. How come it fails? So... Okay, yeah. Are you working on local disk here? Probably. And that's on. Yeah, okay. That's good. Go to the close that one. Go to the chip level design. LCD is on port 2. Yes, port 2. Okay, so now software hardware. LCD should be on the right port 0. Then it should work. So the connections of today, LCD right here, that's port 2. Then basically we'll find the see the port, other port. You can find the ports also in here. Port 0 is the left. No, it's actually port 0 is here. Port 1, port 2 is also here, but you don't use it. It's already there. Then I think the port 1.0 is on this corner, but make you check it from your design. Yeah, good. And then in here you actually have connectors for example, those LEDs here. So you need to make a physical connection by wire from port 1, 0 to LED 1. Okay. Then the and then you need the sleep timer for timing, right? That's a software kind of a nice module. It uses the global resources. Then you need the LED. How many LEDs we have? Only one on this design. You can rename it. It's also a good idea to rename the sleep timer as one as just a sleep timer because of the naming conversion. Okay, tick counter means how big number you can use for the reference number, how many the sleep timer ticks you actually wait. All right. LED 1. Here, of course, you also need to put the parameters. Which port? Which pin? What drive? Okay, active low means that you're, yes. So active low would be, you have the this kind of connection for active low. So you pull it, then this draws current which lights the LED. But we have active high LEDs on that board. Good. What else? LED sleep timer. Pin input. This I need to show you. Pin input is it's easy, but it's not that straightforward. Okay. So basically, configure 1.1 as digital input with the pull down. Descriptive name. Okay, pull down. Okay, so it means the pull down is an input. Okay, so this is the processor inside, and there's a pull down resistor here inside, which is a good idea, since then you can have just a switch here to plus VCC. So that's a button switch. So that kind of switch we have on board. Yeah, SW is this kind of switch. So you can actually pressing the switch, it gives state 1, but this pull down resistor actually gives the initial state 0. Okay. All right. Although these are quite nice instructions what I have there, in any case, I will show you some tricks, since this is not a straightforward kind of thing. At least it wasn't for me. So I have a port 1.1. I would okay. Yeah. What did I have in my exercise sheet? LED is on 1.0. This is the 1.1. on the instructions. Follow the instructions, not what I'm doing here. Okay. Just for fun, I've used some other pin. I use 1.4. So actually, I can change the value here. So it's standard CPU, but it is a pull down kind of in. With the descriptive name, I call it button. That's it. So descriptive name for the input, and then drive is pulled down. The other way around would be to have this pin as high Z and have external pull down resistor. This is more efficient. It doesn't take any resources either. Okay, so now I have the button somewhere. That was what 1.4. Yeah, button. Standard CPU pull down, disabling the initial state 0. That's fine. When I do generate configuration files, we can actually then go to library source files. Oh, was it? Oh, no, sorry. Header files. All the pin information actually is on psoc gpio.int.h. So that gives some mnemonics that you can use on the code. There is actually an application note about this one. Also, did I add the application note? But you have a question, yeah? No internal connections. Only the this. Yeah. Mm-hmm. Are you coming to the PSOC course? Okay. Okay. Haven't seen. Don't know. No, nobody's there. Okay. Okay, so now that's how you would define. Open the external headers. Hey, wait a minute. You first need to click that one. Generate. And then not library, actually. Yeah. Library. Library header files. Yeah, psoc gpio.int.h. That one. Okay. So these are actually just the mnemonics of of those resources what we are using. I have defined this one output H and input H port. So everything is now actually on that file too. Let's go. But the latest one was this button. So all the button definitions are right here. You can actually access those ports also from this say global what are those called? The mnemonics for those ports directly. So I could actually use port 1.4 kind of register names also here. But this is more efficient way, because if you change your mind on which pin it is, you just change the parameterization of the pin. You don't need to touch the code. So changing the pin, then afterwards it's just new parameters, but the code remains the same. So that's why we are using these mnemonics instead. As you can see, those I/O ports are, well, those addresses are actually only to the I/O port address space. So this port input values, what the port actually reads is saved on this button data ADDR register. And that register is, okay, let me go through that one. So that's the variable. You can use it just as a variable. You can read the variable and, for example, compare this button data ADDR to if it's test if it's 1 or 0 by using this mask. So byte data ADDR and button mask would give you the value true or false based on if there's anything on input or not. This here is pragma statement. Are you familiar with the pragma statements? Okay, that's just a compiler directive saying that, okay, this is not a standard C kind of thing, but something else. And in this environment, it means that we can have, or for example, I/O port definitions, since those are on different address space as the normal RAM addresses or ROM addresses. So I/O port is on different address space, and that's the way to tell that the compiler to make all of those accesses using the assembly code that relates to those address space. Okay, nothing more than that, and you don't need to worry about it since this is done already by the compiler. But for you just need to know that, okay, you can read that data from this variable. You can also write the data on this variable on your own risk to change the initial state, for example. But then it wouldn't do anything. If you put the right value 1, it would affect on the output port pin 1.1, and we have a pull down without any energy source here. Okay, and these you can then actually also change the drive mode with if you want to by the software. But we have done it already on hardware on the nice tool. So we don't need to touch those variables. Yes. Yeah, that's yours.
Yeah. But this button, the button part is missing from here.
Oh, you don't have the button yet. Yeah. Okay, you get the button only if you have defined the input. Yes, you need to select one of these pins, either here or there. I use it here, button, and made it pull down. And then when you generate the files, then it actually appears on. Otherwise, you can actually access. It was the name of it was port 1_4. So basically, you could have just replaced the button with the port 1_4. It's exactly the same, but if you have later on changed the port pin, okay, that will make a big difference. You know, rewriting a lot of code or just configuring on that graphic tool. Yes.
When we regenerate the configuration files, does it run over our
Yes. Yes. Except if there are some parts that are user modifiable. By default, you don't modify these files at all.
the main files?
Yes. So drive mode, yes, you can control the drive mode afterwards. Okay, global select. I don't remember what that was. But anyways, interrupt control. So remember there were 4 different ways to do the interrupt, either no interrupt, falling edge, rising edge, or the change from read. So actually they relate exactly to those 2 bits. Those registers themselves, they are 8 bits. Okay. And only 1 bit is for this pin. Then, okay, interrupt enable. So you can, on software, even if you have done the initialization on this graphic tool, you can always overwrite everything what you've done on the graphically by software. Yeah. Okay, and then this actually helps you to select only that pin from the 8-bit port. Good. Alrighty then. So basically on the software, so let me put there, pin input. You can test directly button data, ADDR, and make a bitwise with button mask. This is a test of if this pin or bit button mask is on or off. That's how you check it. This one is true only if there's a state 1 on this pin. Okay. So it's quite easy to use after you understand those mnemonics. So this is actually the variable that holds the full 8-bit port, but only that bit is important. Testing just the button data ADDR in our case actually will result always 1, because that's usually the say floating state of high G input. So any one of those 7 other lines can go high end. Okay, so that's how you test the pin inputs. Good. LED basically works similar to the LCD. On off, read the instructions or the data sheet of that one. And let's see, the sleep timer. There's excellent example on sleep timer on the data sheet. How it works, and basically, if you call the code sample on sleep timer, it gives you the how to use it. So yes, this one uses interrupts, meaning that you have to enable any function or module must be started before you can use it. The starting usually also initializes the module. It starts and initializes. And then we made the sleep timer tick as it was, I think, 512 hertz. You can override it here by software. And but remember to use all the valid numbers. There are 4 different sleep timer settings. Then enable interrupts And this is how you basically use the function for timing. So that one here, sleep timer sync wait 8 ticks at 64 hertz. So basically this one would make it sleep for 8 of these sleep timer ticks. So if the sleep timer would be set to 8 hertz, then it would wait for 1 second. Haha, easy. All right. So I will give you one more hint for the software. So this was just to test if the LCD works. Do all of those tasks one by one. So don't try to do everything at once. And basically do the encapsulation of code. Let me think that this was basically empty when I started, only those couple comment rows. Basically, I would do it not on the first one. On the second row, I would put the initialization or start the modules. So under this one, you have a start of all of those modules. For example, LCD start like that, LED start like that, and whatever your sleep timer start. Also the initializations and such kind of things. After you have started the modules, you could actually do the set up the interrupts on this section, and basically then you might have some debugging like test LCD, just print something on the LCD. Oh, okay, position first. Okay, then say LED, there's the whole part of this one is the test LED. So maybe you can actually just put there value 1 to put it light on or something like that, test. And then, okay, most of the time these programs on microcontrollers, all of the microcontroller programs actually have loop forever somewhere. So if it's designed to do only once, then basically when you have a reset button and it does whatever is needed and does it only once, and what after that, it usually just goes into forever loop doing nothing. But most of the cases, it's the process is circular, so it goes on the beginning after it finishes the stuff. So at some point you have the this working loop. I call it actually this is the my operating system. While one, and then whatever is there. So there is actually a forever loop, which is your operating system. Oops. Simply a forever loop to do whatever is needed. And what to do there? There was that blinking LED, or actually there was the task 1, task 2, and task 3. Task 2 kind of thing task 3 kind of thing. Was the task 4? What was the task 4 actually? Um, LCD pin input. Ah, if needed. Well, okay. But anyways, encapsulate this somehow that it makes more sense. So start with the comment lines, like turn on LED or read the input port or button. Then or just turn LED on or off, update LCD value, print out, and then maybe sleep 4.5 sec. Okay, so idea would be to first write the idea of your code as comments, and then you start filling in the comments. At the same time, you get also documentation of the code. So documentation first, what you are intending to do, what this program should do, and that gives you the good foundation for making even bigger programs. There, good. Any questions? So what is the deadline for the first exercise is probably the first question. Saturday afternoon. This week, Saturday afternoon. I want your first exercise before I leave. Just in case, there are some, small things there, here and there, small details. I want to give you the first feedback before I leave. So, yeah. So I have given you now enough of information so that you can survive the first exercise. And yes, you can work on pairs. Now we can, I wouldn't say don't work in a group. There'll be, you can work on pairs. Team up, it's a good thing actually. Also, I created a, I have no idea if it has any use of it, but say social network. Since we have some students, Arvi is not the only one who is taking the course. There are also some, say, five other students in Metropolia who couldn't come here now, but they are still, we are continuing this the course for a while. So they are actually doing their things there, and you will be doing here. So making any, team effort would require some social network kind of thing. I created a Google kind of thing there. I have no idea if it's used in any use or not. But to add you to that circle, I would need your Google account. I think Google the Gmail address. Fundamentally, I can add you there. You can use that one, or you can actually make your own Facebook private group, whatever is your favorite platform on social networks. I don't have favorites on social networks. I'm not social person. I'm not that social. Okay, but anyway, so maybe you can at some point discuss about what could be used, what is used in Frankfurt usually, and what is used in Finland. So it would be a good idea to have a discussion group also, but only if you think that it's used. Okay, excellent. So yeah, that's my show of today. That was longer than usually. So usually I have a shorter the show. Well, uh, give you more time to do the exercise. But this is the fundamentals, very basic level, and also making sure that everyone has more or less uh, in, the required information to survive the first exercise. Okay, yeah, I'll do some update uh, of the website, but anyways, you can start working on the exercise one alone or together, and I think this is just about the time also to get a lunch or something. So I will be here until 4 o'clock, something like that, until 3 or 4. I have no idea. I have nothing else to do here. Okay, good. Thank you. Yes, every day this week at 9. Is the 9 o'clock good time? Good. 9 o'clock that is. Yes. It's up to you. My show is usually about 1.5 hours. The rest of you should use that time for you as you see it the best. So I give you a lot of self-responsibility here. Okay, I'm not watching over your shoulder unless you have some problem. If you have a problem, then I will be here to help you on those. Good. Any other questions? Okay. Oh, yeah, sure, no problem. That's my program currently. It doesn't do much at all. Mhm. Okay, so yeah, one more question. Yes. Uh, hmm? Yeah, okay, okay. Yeah, I will show you. So first, go and find your working directory. That's where you start. I think I have my own. Let's see. Usually it's on documents. I have the SOC designer projects file and uh, any one of these. Yes, that one. Created today. That must be it. No, that's not it. Where is that project file? Today's 7th, right? No, it's no, fourth. Okay. Yeah, 2017. Date modified. Let's put it on the other. Okay, that one. SOC EX1 anti-KP. Yeah. So make a zip of that one. Oh, sorry. Okay. I have two displays here, one for monitoring. There, the better. So just basically in my computer, I just make an archive like that. On those, you have your zipper, some sort of zipper there. So you just compress your VSOC, blah blah blah. Where's the zip? Yes. Yeah, that's it. Then go to your favorite the cloud service, Dropbox. I use personally a Google Drive. Let's see, where could I? Okay, that's my Google Drive. I'll show you. Okay, that's just my Google Drive here. For example, let me make a new folder here. Hmm. Full bar is a nice name. and drag and drop, uploading. To be able to actually share it, click the sharing settings. Get shareable link is not enough. You have to also turn on the link. And this is not enough either. You need to actually go to sharing settings and make sure that anyone with the link actually, in my case, I'm using the Metropolia Google account. It means organizational. I had to separately select allow external access. Done. Okay, now, well, the link. Get shareable link. Yeah, link copy to clipboard. And that's the link what you put there. If you want to make sure that it's okay, it opens okay, send that link to your friend, and he should be also able to open it. Yeah, or then have a incognito window to check it. Yeah. Yes. Let's see. On the project, the link to the report would be the similar, but you would do the Google site for that one. So for the exercise, you have this is the most important part. Let me see what I'm expecting there. Yeah, report. Project files is the report. Yeah. Link to your project files and link to your main.c. Yeah. There's a reason for it. The reason is actually, this is my favorite way of doing it. I copy and then go to the Google Drive again. Yes. Where's this full bar? There's my full bar. Make a new file, Google Doc. For example, like that. And again, share it so that anyone with a link can comment. This is the feedback channel. So I can give you comments if it's, bad or good or bad coding. Otherwise, I don't have any, I don't want to send such emails. My email is full enough. so basically, I just, again, that one there. Copy, allow external address, and let's see, can comment, not edit, but comment. I don't want to edit your code. And copy and then done. Well, if you start, well, it depends. It's something like a few hundred megabytes, depending. Depending on the total load of the networks what you are using, it depends. Yeah. I have no idea. I'm not a local, so local storage. Maybe I don't know. Okay. Do you have the installation files? You actually downloaded those yesterday. You just need the memory stick. That's the fastest way of transferring, few hundred megabytes in a few seconds. Yes. You will do it on your own Google Drive. Yeah, own drive. That's my drive. Don't use that one. Use your own. Yes, link to me. Good. But most importantly, actually, do the exercise. Then we can actually look at together how to make it if you're not too familiar with the sharing the stuff on these cloud services. Yeah, yeah, yeah. It's not a big deal. I can show you. Then you know. Then you can show it to others. Yeah, that's all. I didn't know about any of those cloud services 10 years ago. Oh, 10 years ago we didn't have any. But it's simple. Actually, it's a big fuss about these cloud services. Actually, cloud services has been there since we have networking overall. But we are just calling it as cloud services. So, for example, if you're using your own computer, then you can actually install it's not anymore the Google Drive. It's called what? Let's see. It's now they have nice Google software which is called Google Drive File Stream. If you install that Google Drive file stream, then it's as any file system on your computer. And then you just need to, use the browser to get these shareable links and that kind of things. But it's I don't know. There's a lot of mystic put on very simple things. But I can get you started with this. Okay. Good. Anything else? I'm hungry. Okay, good.